part of this problem is going to be find the vector B2. What does our magnetic field do to wire 2? So here we have wire 2. We know that the magnetic field is going to make big circles around the wire. The wire is at the center. We want to draw our circle so that it cuts through point P. So we'll draw a circle here. The magnetic field at point P is going to be a tangent to the circle. So let's get the orientation. Thumb goes with the current into the page and our fingers come around this way. So the orientation of the magnetic field everywhere goes this way. At point P, it's a tangent. Sometimes those tangents can be a little tricky to draw. So sometimes it's a little bit easier to draw in our R first. So R comes from the wire to the point. So here's R2. And then if our magnetic field is a tangent to the circle, it means it's perpendicular to R2. So let's get a line in there that's perpendicular to R2. So now our B2 point this way. We know it's going to point down because we're coming tangent to the circle and our fingers point down and away at this point. So here's our vector B2. We can get our angles in here if we wish. So we have here, this side is 10 centimeters, this side is 10 centimeters. This is a right angle, so our angle theta in right here, tan theta equals opposite over adjacent, 10 centimeters over 10 centimeters equals 1. So theta is the inverse tan of 1. That's 45 degrees. If this angle is 45, it means this angle is also 45 because the magnitude, the vector B has to be perpendicular to R. Perpendicular means they add up to be 90. So if this is 45, then this is also 45. So now we know the direction of B2. Let's go ahead and find the magnitude of B2. So the magnitude of B2, we'll use the same equation, mu naught I2 over 2 pi R2 for the magnetic field around a long straight wire. Next we'll plug our numbers in. So mu naught is 4 pi times 10 to the minus 7 Tesla meters over amps times the current, 1.25 amps. So both of these wires had exactly the same current. That's why we're using the same value. Divided by 2 pi times R2. Now we'll ask, what is R2? That's the hypotenuse of a right angle triangle. So let's calculate our R2. We'll do that on the side over here. So R2 is going to be the square root of 10 centimeters squared plus 10 centimeters squared. The square root of 10 squared plus 10 squared is 14.1 centimeters. There's our R2. So 2 pi times R2, 0.141 meters. So there's our magnitude of B2. Let's do that through the calculator, and we get 1.77 times 10 to the minus 6 Teslas. So there's our B2. We'd like to break this into components. Let's just do a quick sketch of that one again in case we need a little bit of help breaking it into components. There's B2. B2y points down. B2x points to the left. And this angle is 45 degrees. So our B2x equals minus, because it points left, B2 times cosine 45 degrees. Put that through the calculator and we get minus 1.25 times 10 to the minus 6 Teslas for our x component. B2y equals minus, because it points down, B2 times sine 45 degrees equals minus 1.25 times 10 to the minus 6 Teslas. So there's our two vectors, B1 and B2. Next, to finish, we're going to find the net magnetic field by adding those two vectors.